Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. In my last class, I discussed the concept of Bayesian decision theory. In Bayesian decision theory, I have to estimate the probability of Wj given x that I have to determine. So for this, I need two information. One is the probability of x given Wj, that is called likelihood, and also the probability of Wj, that is called the prior. So this information I need. The probability of x given Wj, that is the class conditional density or the likelihood, and suppose this information is available, that means the density of the likelihood function or the class conditional density is available, then this is called the parametric method. That means the density from of the likelihood function or the class conditional density is available, but the parameters are not available. So suppose if I consider a Gaussian density, in Gaussian density there are two parameters, one is the mean, another one is the variance. And if I consider high dimensional case, then it is the mean vector and the covariance matrix. So in case of the parametric method, this density from is available. I know the density of probability of x given Wj, so that information is available, but I do not know about the parameters. So I have to estimate the parameters. So there are two methods, very popular methods. One is the maximum likelihood estimation, another one is the Bayesian estimation. So by using these two techniques, I can determine the parameters. The parameters are mean and the covariance. Another case is, suppose the density from is not available. The density from of class conditional density is not available, that is the probability of x given Wj. So that is not available. We have to estimate the density. So there are two popular techniques, one is called the Parjan window technique and another one is called the k nearest neighbor technique. So by using these two techniques, I can determine the density of probability of x given Wj, that is the likelihood. So in this class, I will discuss the parametric methods. First I will discuss the maximum likelihood estimation, and after this I will discuss the Bayesian estimation. After this I will discuss the non-parametric methods. One is the Parjan window technique and another one is the k nearest neighbor technique. So let us discuss about this parametric and the non-parametric methods. So the first one is the parameter estimation. So I told you that what is the parametric method. In case of the Bayesian decision theory, so I have to determine this, the probability of Wj given x, that I have to determine, and that is nothing but the probability of x given Wj, that is the likelihood, and the probability of Wj, and j is equal to 1 to c, probability of x Wj, probability of Wj. So in this case, what information is available? So in this case, if I want to determine the probability of Wj given x, that is the posterior probability. So suppose the density from of the class conditional density is available. So suppose the density from is available. So density from is, suppose it is the parametric from. In case of the normal density, I have two parameters, one is the mean vector, another one is the covariance matrix. So this parametric from is available. If you see this formula, so for calculating probability of Wj given x, so what information I need? I need the information of probability of x given Wj. That information I need, that is nothing but the class conditional density, and the parameters are, suppose, the mean vector and the covariance matrix. So this information also I need, the mean vector and the covariance matrix also I need. So that means I have two parameters, the parameters are theta I1 and theta I2, suppose. So two parameters I need, and also I need the information of how many classes. So classes is 1 to c number of classes. So here you can see this is j is equal to 1 to c. So c number of classes. So this information I need. for calculating probability of Wj given x. So one is the class conditional density, that is the probability of x given Wj, that information I need. And I have two parameters, the one is the mean vector, another one is the covariance matrix. And also I need another information, that is number of classes, j is equal to 1 to c. So that information I need to calculate the probability of Wj given x. So this information is not available directly. So for this, actually we have the training samples for all the classes, that is nothing but the supervised training. So for each and every classes we have the training samples, and after this, from these training samples we have to do the estimation. Estimation is nothing but we have to estimate the parameters. So parameters are the mean and the covariance. So we have to estimate the parameters. And in this case, in case of the parametric approach, the PDF from is known. That means I know the PDF of the class conditional density in case of the parametric from. So I can write this in parametric approach. In parametric approach, that is the PDF from is known, but the parameters I have to determine. The PDF from is known, but the parameters I have to determine, I have to estimate. That is the parametric approach. What is the non-parametric approach? In case of the non-parametric approach, the PDF from is not available. That means I have to estimate the density. That is nothing but the density estimation. So in case of the non-parametric method approach, the density from is not available, so we have to estimate the density. So for this we need the training samples, for all the classes. So if I consider the training sample, suppose xn, that belongs to a particular class, suppose class is Wj, that is available. That is, the training samples are available corresponding to a particular class, and that is nothing but the supervised learning. That is nothing but the supervised learning. So for estimating the probability of Wj given x, that is the posterior probability, I need the information of the prior probability of Wi, and also I need the information of the probability of x given Wi, that is the class conditional density. So I need this information, and also I need the information of number of classes. So we have C number of classes. So based on this, I have explained two approaches. One is the parametric approach, another one is the non-parametric approach. So in this case, what I am considering, suppose the density from is known, that is the class conditional density. So density from is known, but I have to estimate the parameters. So in this case, there are two parameters, one is the mean, another one is the covariance. So one is the mean vector, another one is the covariance. So suppose this is theta1 and this is theta2. So for this I can apply two popular techniques. One is the maximum likelihood estimation, another one is the Bayesian estimation. In case of the non-parametric method, the density from is not available, but I have to estimate the density. So you can see, so for estimation techniques, that is the parameter estimation techniques, I may consider this popular method, that is the maximum likelihood estimation, and also I may consider the Bayesian estimation. So in both the cases, results are nearly identical, but the approaches are different. In case of the Bayesian estimation, the computational complexity is more as compared to maximum likelihood estimation. In case of the Bayesian estimation, I have to determine the multidimensional integration. So I will explain this, but in case of the maximum likelihood estimation, I have to determine the differentiation. So that is why if I consider the computational complexity, then Bayesian estimation, if I consider that it has more computationally complex as compared to maximum likelihood estimation. So, in case of the maximum likelihood estimation, parameters in maximum likelihood estimation are fixed but not known. And in this case, what I have to consider, I have to maximize the probability of obtaining a given set. Suppose H is the training sample, or maybe I can consider probability of D. D is the training set given theta. So, I have to maximize this probability of D given theta, that theta is fixed. So, parameter estimation that maximize a likelihood function that I can consider. Maximize the probability of obtaining the given training set. So, I have to maximize this. So, maximize the probability of D given theta in case of the maximum likelihood estimation. That means maximizing the probability of obtaining the given training set. And in this case, the theta is fixed. Theta is the parameter vector. Now, let us see the mathematics behind the maximum likelihood estimation. So, what is the maximum likelihood estimation? So, in case of the Bayesian distance theory, we have to estimate this, the probability of Wj given x, we have to estimate. And for this, you can see, I need the information of this x given Wj, that is the class conditional density, and also the prior. And if you see this is the evidence, j is equal to 1 to c, probability of x given Wj, probability of Wj. So, in this case, the probability of x given Wj, so this parametric form, the parametric form that is available, that is the, suppose if I consider the normal distribution, that information is available, that is the parametric form is available, but the parameters are not available, but the parameters we have to estimate. So, in case of the normal distribution, I have two parameters, one is the mean, another one is the covariance. So, if you consider this one, the theta j, that is the parameter vector. So, I have two parameters, one is the mean vector and another one is the covariance matrix that I have to determine. So, if I want to show the maximum likelihood estimation, so suppose we have the training samples, the training sets D1, D2, so DC, that means we have the training sets and we have the training algorithm is available. And we have to estimate the parameters, we have to estimate the parameter vector, and what information is available? I know the density from, that is the class conditional density is available. This dependence on the training set, I can write like this, the dependence on the training set, I can write like this, the probability of x given Wj theta j, that is the dependence on theta j, that is I am considering the class conditional density and I am showing the dependence on theta j. So, the problem is to determine unknown parameter vectors. So, that means I have to determine theta 1, theta 2 from the information of the training data set, because we have the training data set for all the classes, and from this training data set I have to determine the parameters. So, that is the parameter vector I have to estimate, and in this case I am considering the independent data set. So, what do you mean by independent data set? So, suppose I am considering the data set D1, that is for the class W1. Similarly, if I consider another data set, that is D2, that is for the class W2. Like this, if I consider another class, suppose So if I consider the data set, suppose the training data set is DI, and suppose I have the samples are x1, x2 like this. These are the samples, and corresponding to this the class is Wi, and suppose the class is another class is Wj. So this training data set Di is for the class Wi. This is not for the class Wj. This is not for the class Wj. The training data set Di is for the class Wi. It is not for the class Wj. That is the supervised training. That is the concept of the supervised training. So here x1, x2, these are the samples. These are the samples of the data set. The data set is the Di, and the samples are drawn independently. The samples are drawn independently. So I have the training data set, that is D1, D2, DC. Then what is the probability of D given theta? That is nothing but this product. So suppose I have these training samples x1, x2 up to xn, suppose xn. So xn and theta. So I have to maximize the probability of D given theta. So that I have to maximize. So that is the concept of the maximum likelihood estimation. So that means again I am writing, so I have to maximize the probability of D given theta. The probability of obtaining a given training set for the parameter vector is theta. Now I am defining one likelihood function. The likelihood function, that is the log likelihood function I am considering. Likelihood function I am considering. So L theta, that is the log likelihood function. That I am considering, that is the log likelihood function. And after this, what I am considering? I am considering the differentiation of this likelihood function. And suppose I am getting the approximate value. So I am just doing the differentiation because I have to maximize this one. So it is equal to 0 because I have to find the maximum of this. So what is this operator? So if I consider this operator, this is the partial derivative I am considering with respect to theta 1 like this, with respect to theta 2. So suppose I have these parameters theta 1, theta 2, theta p like this. So I have to find the global maxima. Maximum I have to find in the parameter space, parametric space. So global maxima I have to find in the parametric space. So from this equation, if I see this equation, so from this equation I can determine the parameters. The parameters are like this. This is a parameter vector. So I can determine theta 1, I can determine theta 2. So in case of the normal distribution, this is the mean vector, and also this is the covariance matrix I can determine. So what is theta? The theta is nothing but this is the parameter vector theta 1, theta 2, theta p transpose. So by considering this equation, I can determine the parameters. So for example, I can determine the mean of the samples. So it is the mean of the samples you can determine by this equation. So it is the mean is something like this. This is nothing but the arithmetic mean of the samples. The arithmetic mean of the samples. And also I can consider the maximum a posterior probability, that is the estimation, maximum a posterior estimation, that is the MAP I can consider. So MAP is nothing but the likelihood function I am considering, that is the L theta, that is the likelihood function, and the prior information also I am considering, P theta. So I have to maximize the probability of theta x, probability of x theta p theta px. So for flat prior, so if I consider the flat prior, the maximum likelihood estimation will be same as that of the MAP, maximum a posterior probability estimation. So if I consider the prior is flat, so this is the prior information. So suppose for the flat prior, the maximum likelihood estimation is equal to MAP, the MAP estimation. So this is the basic concept of the maximum likelihood estimation. I am not explaining how to determine the parameters, but based on this equation, so if you see this equation, I can determine the parameters, all the parameters. So this is the fundamental concept of the maximum likelihood estimation. The next one is the Bayesian estimation. In case of the Bayesian estimation, we can consider the parameters as random variable having some known distribution. In case of the Bayesian learning, I am repeating this. What I am considering, the parameters are random variable with some known a priori distribution that is available, that information is available. This training samples allows the conversion of the prior information into posterior density. So the training samples allows conversion of prior information into a posterior information. So in case of the Bayesian estimation, in case of the Bayesian learning, what I have to consider, I have to maximize the probability of theta given d. So d is the training set and theta is the parameter vector. In this case, the theta is the random variable. So that means we have to determine the density that approximate an impulse. So briefly I will explain the mathematical formulation of the Bayesian learning. So what is Bayesian learning? You can see in case of the Bayesian learning, again I am showing the Bayesian decision theory, that is the Bayes law I am writing. The probability of Wi given x, d is the training data set. So that means I am considering the dependence on the training data set, that is the dependence on d is equal to probability of x Wi d, that is the class conditional density, and I am writing d because this is the dependence on the training data set. I is equal to 1 to c probability of x given Wi d, probability of Wi given d. But in this case, the prior information is known, the priori information is known. So I can write like this now, the probability of Wi given x d probability of x given wi, d the probability of wi, and summation I is equal to 1 to c probability of x wj d probability of wi and probability of wi. So I can write like this. So in case of the Bayesian estimation, I have to determine what I have to determine. I have to determine the probability of x given d, that I have to determine. So what information is available? The information is the probability of x that is not available, this is unknown, that is not that is unknown, and the parametric form is known. The parametric form is known. So that means the probability of x given theta, that is known, and also the probability of theta, and that is known, So this, the training data set converts the prior information into the posterior information. The p theta is available, that is known, but the training data set converts the prior information into the posterior information. So I have to determine the probability of x given d, I have to determine. That is nothing but probability of x given theta and probability of theta d theta. So this actually I am obtaining like this, the probability of x given d is nothing but probability of x theta d theta. So that is available. So this probability of x theta d is nothing but probability of x theta d probability of theta d. I can write like this. So that means from this actually I am getting this one. From this I am getting this one. Probability of x given d. Now because this is the important equation, so probability of x given d is nothing but probability of x theta probability of theta d theta, that is available. So I have to maximize the probability of theta d. So maximize probability of theta d, I have to maximize, and in this case the probability of x given d will be approximately equal to probability of x this is approximate value of theta, that is the parameter vector approximate value of theta. So that means I am taking average of probability of p x theta, because in this case I have to maximize this. So that means I have to maximize this. So it will be a Dirac delta function corresponding to the estimated value of theta. So this is the approximate value of theta. So I have to maximize this probability of theta given D. I have to maximize. So that means the probability of x given D is nothing but probability of x given theta. That means I am taking the average of P x given theta. So this integration, if you see this integration, that means I am taking the average, and this is the multi-dimensional integration. So it is very difficult to determine because it is computationally complex to determine the multi-dimensional integration. So something like the Monte Carlo simulation technique I can use to determine this integration. And here you can see with the help of the Bayesian estimation I can determine the probability of x given D. So that I can determine. And after this I can determine the parameters. The parameters are theta. The parameter vectors are theta. So this is the basic concept of the Bayesian estimation. So both the methods, the maximum likelihood estimation and the Bayesian estimation, they will give almost similar results. So briefly I discussed the concept of the maximum likelihood estimation and the Bayesian estimation. So for more detail you can see the book Pattern Classification by Duda and Hart. That book also you can see for this maximum likelihood estimation and the Bayesian estimation. Now I will discuss the concept of the non-parametric methods. In case of the non-parametric methods, that already I have explained, that is the density from is not available, but we have to estimate the density. And there are two techniques, one is the Parzan window technique and another one is the k nearest neighbor technique. These two techniques I can consider. So in case of the generative models, we assume that the data to come from a probability density function. That means we have this information, the probability of x given Wj for the generative models. But in this case, sometimes this density is not available, that information is not available. So we have to estimate the density. So how to estimate the density? So I will explain these two techniques. One is the Parzan window technique, another one is the k nearest neighbor technique. So in case of the non-parametric procedure, what we can consider, we have to estimate the probability of x given Wj. That means we have to estimate this. But in case of the k nearest neighbor technique, we can directly estimate this density, because what is the ultimate objective? The ultimate objective is we have to determine the probability of Wj given x. That is the posterior probability I have to determine. So the basic idea in density estimation is that a vector x will fall in a region R with a probability. That probability I am determining. P is a smooth or the average version of the density function. So density function is Px. Suppose n samples are drawn independently and identically distributed, that is the IID, according to Px, that probability Px. The probability that k of this n, the k number of samples out of n number of samples fall in the region R is given by this distribution. That is a probability of Pk I can determine. That is nothing but the binomial distribution. So what I am considering, the probability that the k number of samples out of n fall in the region R. And from this I can determine the expected value of k. So I can determine expected value of k, Ex is equal to n into P. And if I consider the maximum likelihood estimation, so by the maximum likelihood estimation I can determine or I can maximize the probability of probability Pk for the given theta, that I can maximize, and corresponding to this I will be getting the probability. The probability is nothing but P is equal to k divided by n. So n is the total number of samples I am considering. So therefore, with large number of samples, the ratio k divided by n is a good estimate for the probability P, and hence for the density function is Px. So that means this ratio k by n gives the estimate of the probability. The probability is P. So here n is the total number of samples and k is the number of samples within this particular region that I am considering. And that this ratio k divided by n, it gives the probability is p. And if I consider the px is continuous and the region is so small that px does not vary significantly within it. So I am considering this case, that is the px is continuous and that the region R is very small, very small. Then in this case the px does not vary significantly within it. So for this I can write like this. So integration px dash dx dash is approximately equal to px into v. So I will be getting this. And from this expression, from the previous expression, because if you see the previous expression is the probability is nothing but k divided by n, and now I am getting this probability, the px is nothing but k divided by n divided by v. So by using this expression I can determine the density. The probability x, that is the density, is equal to k divided by n divided by v. So v is the volume enclosed by the region R. So R is the region I am considering and v is the volume enclosed by the region is R. So by using this expression I can determine the density px I can determine. Now in this case, however, v cannot become arbitrarily small because we reach a point where no samples are contained in v, and in this case we will not get the convergence. The v cannot be very small. Suppose if I consider the volume is very small, then in this case what will happen, it may not enclose any samples. Then in this case you cannot determine the density. So what approaches I can consider? V cannot be allowed to become small since the number of samples is always limited, because we have the limited number of samples. So V should not be very small, otherwise we cannot expect that the samples will be available within this particular volume. The volume is very small. And another case is we have to consider the certain amount of variance in the ratio k divided by n. So we can consider this. That means the volume should not be very small because we have the limited number of training samples, and also we have to consider the certain amount of variance in the ratio is k divided by n, that we can consider. So you know this expression, the probability of x, that is the density, k divided by n divided by v. So in case of the Parzan window technique, fix the volume of the region v and count the number of samples k out of n number of samples falling in v. So that means the volume is fixed and we have to count the number of samples within this particular volume. The volume is v. So k number of samples within this particular volume out of n number of samples. So total number of samples is n, and I am counting how many samples are within this particular volume. So k number of samples within this particular volume. So from this information you can see k divided by n divided by v. From this information I can determine the density. That is called the Parzan window technique. In case of the k nearest neighbor technique, the volume is not fixed, but I can consider the k number of samples. So suppose it is fixed, suppose I am considering 5 number of samples. So I have to increase the volume so that it encloses the 5 number of samples, that means the k number of samples. So first volume it encloses 1 sample, suppose. The second volume it considered suppose 2 number of samples, and third volume if I consider, it encloses 2 samples. So how many samples? Total samples 5 number of samples enclosed by this volume. So that means I am increasing the volume, I am growing the volume so that it encloses the k number of samples. In case of the Parzan window technique, the volume is not the volume is fixed, and I have to count the number of samples k within this particular volume. In case of the k nearest neighbor technique, the volume is not fixed and we have to increase the volume so that it encloses k number of samples. And from this information I can determine the density. The density is px is equal to k divided by n divided by v. So by using this expression I can determine the density. So for estimating the density, what I am considering, so to estimate the density of x, we form a sequence of regions we can consider the regions R1, R2 like this containing X. The first region contains one sample, the second contains two samples and like this, and Vn be the volume corresponding to the region Rn, and Kn is the number of samples falling in the region Rn. So, I am considering the K number of samples falling in the region Rn, and in this case I can determine or I can estimate the probability or the density Px. So, the Pnx be the nth estimate of the probability is Px. So, I can determine the density is nothing but Kn divided by n divided by Vn. And if I consider suppose the unlimited number of samples, so many samples if I consider, then what convergence I can get? The Pnx converges to Px. So, if I consider large number of samples, then the Pnx approaches Px. But in this case, in case of the Parzan window technique, we have to consider these three conditions. One is the limit Vn n tends to infinity should be equal to 0. So, that means what is the meaning of this? The volume may be very small because I am considering large number of samples because n tends to infinity. Then in this case you may expect some samples within this particular volume, the volume is suppose Vn. The volume Vn may be very small because I am considering very large number of samples we are considering. So, that means you may expect some of the samples within this very small volume, the small volume is Vn. So, this is the first condition, that is the limit n tends to infinity Vn is equal to 0. The second condition is limit Kn is equal to infinity, n tends to infinity. Since we have large number of samples, so that means the Kn will be also very large. Since the n is very large, so that means the Kn is also very large. And if I consider the ratio Kn divided by n tends to infinity, that is the limit, then in this case this ratio will be 0, tends to 0, because n is very high as compared to Kn. So, that is why this Kn divided by n, that ratio limit n tends to infinity should be equal to 0. And there are some mathematical derivations in the case of the Parzan window. So, I can determine the density can be estimated by using this equation. So, you can see the book by Duda and Hurt, the pattern classification by Duda and Hurt, and you can see the derivation of this equation. So, by this equation you can determine the density. Now, let us consider the k nearest neighbor technique. So, in this case we have to estimate the density using the data points, and let us consider the cell volume to be a function of the training data, and in this case the center a cell about x, and let it grow until it captures Kn number of samples. So, here you can see the cell volume be a function of the training data. And what I am considering, I am growing the region, that means I am increasing the volume so that it encloses the Kn number of samples. So, it encloses the Kn number of samples. So, Kn is a function of n is the total number of samples. So, Kn are called the Kn nearest neighbor of x, that is the Kn. And two possibilities can occur. The density is high near x, therefore the cell will be small, which provide good resolution. So, density may be high near the Fisher vector is x, and in this case therefore the cell will be small, which provide good resolution. In the second case, the density may be low, therefore the cell will grow large and stop until higher density regions are reached. So, that means I have to increase the volume so that it encloses Kn number of samples. So, density is low, therefore the cell will grow large and stop until higher density regions are obtained. So, this is the two conditions of the k nearest neighbor technique. So, mathematically you can see, so directly we can estimate this posterior probability Pn Wi given x, directly we can determine from the n level samples. So, we have the n number of samples are available, and these are level samples, that means I am considering the supervised training. Let us place a cell volume V around x and capture k samples, and ki samples amongst k turn out to be label wi. So that means I am considering ki number of samples corresponding to the class is wi. So total number of samples are n, and I am considering ki number of samples corresponding to the class is wi. So from this you can determine the density. The density is Pn x comma wi ki divided by n divided by v, that you can determine. And from this you can see I can determine the posterior density Pn wi divided by x, that I can determine. So if you see this equation, so what I am determining already, Pn x comma wi, that I have determined, that is nothing but ki divided by n into v, and you can see the summation I am taking, that is the evidence, and I will be getting the ratio is ki divided by k. So what is the ki samples amongst k? So k number of samples I am considering, but ki samples corresponding to the class is wi, and I am considering the total number of samples. The total number of samples is n. So this ratio, the ki divided by k, that gives the information of the density, that is the posterior density. So it gives the information of this. So we have to determine the ki number of samples corresponding to the class is wi. So if I can determine the ratio ki divided by k, if I determine this ratio, then I can determine the density. The density is Pn wi given x, that I can determine. So this process, the kn nearest neighbor algorithm, that is the classification algorithm, I can show pictorially like this. Suppose I want to classify a new data point. So a new data point is this, and I have two classes, the category A and category B, and this is before k nearest neighbor. And after this, based on the minimum distance, the new data point is assigned to the class is A. So that is category 1. Category 1 means the class A. So based on this, you can see this new data point is assigned to the category 1. So this is the k nearest neighbor algorithm. Again I can show what is the k nearest neighbor algorithm. Here you can see I am considering three classes. So one is the yellow, one is the green, and one is the orange. And I am considering one new data point. So this is the new data point I am considering. And I am finding the distance between this data point, the new data point, and the other samples corresponding to different classes. So one class is the yellow class, another class is the green class, another class is the orange class or the red class. So you can see I am finding the distance is 2.1, 2.4 like this. I am determining the distance. So corresponding to this yellow one, you can see the distance is 2.1, that is the first nearest neighbor, the distance is minimum, and again corresponding to the second one, the second data point, that is the yellow one, the distance is 2.4, that is the second nearest neighbor I am getting. And again if you see this green one, so corresponding to this green one, the distance is 3.1, that is the third nearest neighbor. And again you can see the distance between the gray point and the orange or the red point, so it is 4.5, that is the fourth nearest neighbor. And in this case we have to determine the number of votes. So corresponding to this yellow, how many votes, because 2 times it is the nearest neighbor, so 2 votes I am getting. Corresponding to the green, I am getting 1 vote. Corresponding to the orange, I am getting 1 vote. So I can count the number of votes, and based on this the new data point can be assigned to a particular cluster. Again I am showing this one. So this new data point I have to classify, and for this you can see I have two classes, the class A and the class B, and based on the minimum distance this new data point can be assigned to a particular class, the class A and the class B. So in this class I discuss the concept of the Bayesian decision theory, and after this I discuss the concept of the parameter estimation. In the parameter estimation I discussed two algorithms, very popular algorithms. One is the maximum likelihood estimation, another one is the Bayesian estimation. So briefly I explained these two concepts. After this I considered the case of the non-parametric estimation. In case of the non-parametric estimation, I have to estimate the density. So for this, I consider two algorithms. One is the Parzan window technique, another one is the k nearest neighbor technique. So briefly, I explain the basic concept of the maximum likelihood estimation, Bayesian estimation, the Parzan window, and the k nearest neighbor technique. For more detail, you can see the book Pattern Classification by Duda and Hurt that you can see. So let me stop here today. Thank you.